Hello class, welcome back. Today we will talk about valence electrons. The electrons in all the subshells with the highest principal energy shell are called valence electrons. So for example, we have the electronic configuration. Let's look at the electronic configuration for, let's take sodium. It's 1s2, 2s2, 2p6, and 3s1. So you see, the highest principal energy level for sodium is 3s in this electronic configuration. So this electron is sodium's valence electron. That's what we mean. The electron in all subshells with the highest principal energy level. Sodium has only one subshell. That's why we took only one. But if you have a p subshell and electrons are there, if we have 3p subshell and electrons are there, we include all the electrons. Okay. Electrons in lower energy shells are called core electrons. One of the most important factors in the way an atom behaves, both chemically and physically, is the number of valence electrons it has. The number of valence electrons affect the property of the element. So let's look at some valence electrons. Valence electrons. This is krypton. It has 36 electrons. Let's see its electronic configuration. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. The highest energy level are 4, you see. So the number of electrons in this highest energy level are 2 plus 6. Those are krypton's valence electrons. 2 plus 6 equals to 8 electrons. So the valence electron for krypton is 8. And we have 28 core electrons and 8 valence electrons. Let's look at rubidium. It has 37 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. So the highest is 5. The highest energy level is 5. And the number of electrons it has is 1. So the core electrons are 36. And the valence electron is 1. So that is how you can determine the valence electron. Electron configuration and the periodic table. Let's look at electron configuration and the periodic table. How is electron configuration connected to the periodic table? How can we use the periodic table to predict the electron configuration? The periodic table is divided into blocks, S, P, D, and F blocks. We need to know that. For the S and P blocks, the period number corresponds to the principal energy level of the valence electrons. For the S and P blocks, the period number corresponds to the principal energy level of the valence electron. For the D block, the period number corresponds to the principal energy level minus 1 of the valence electron. The principal energy level minus 1 of the valence electron. So this is our periodic table. You see, look at the S block, 1, 2, S block. Then here, this is the D block. Then we have the P block here. Then we have the F block. So electron configuration from the periodic table. We can use the periodic table to write the electronic configuration for P, for phosphorus. So this is P. How do we write the electronic configuration? You have to, so this is S. This is one S. This is one S. So you notice that S block has two boxes which represent 2 electrons. The boxes represent electrons. So this is 1 electron, this is the second electron. Then the D block, you see the D block has 10 boxes. These boxes represent electrons. The P box has 6 boxes which represent 6 electrons. So we can start by writing the electronic configuration, but we have to end at this block. So we are going to start from here. You see, this is the principal energy level. These numbers represent the principal energy level. So if we want to write the electronic configuration for phosphorus using the periodic table, we'll start counting for here. You see, this is 1, counting here, 1. And how many blocks does he have? This one to represent the S. This is 1S. So you see, we have this 1, we'll put 1. And how many boxes do we have? 1 and 2. So this is S. The boxes represent electrons. So 2S. Then we go to this period 2. So we are going to write 2. So S is 1, 2 block. So S, which represents 2 electrons. Then we go here. We have this 2, and this is the P block. We count 1, 2, 3, 4, 5, 6 electrons. We have to do that until we get to phosphorus, until we get here. Then now we go to the 3. We write 3, S, 2 electrons. We have 2 boxes, 1, 2. I should be crossing these boxes. Two. Now there is nothing in the D. See, it's empty. So we go to 3P. We are going to count the boxes until we get here. 1, 2, 3. 3. So this is the electronic configuration of phosphorus, which we have written using the periodic table. Let's take another example. Clean this one. want to write the electronic configuration of neon. So we are going to start again, start from here, mark the boxes until we get to neon. Electronic configuration of neon. So period 1, which is principal energy 1, 1s. So we count the number of boxes which represent the electrons. We are going to put 2. Then period 2, we count the number of boxes, which is 2s. There's 2 electrons, we put 2. You see, we go to 2p. How many boxes until we get here? 1, 2, 3, 4, 5, 6. We put 6. So this is the electronic configuration for neon. We'll do one more example before we have done for phosphorus, we have done for neon. Let's try and do for, I don't know what this element is. I'll just put element. Or I can check. But I'm concerned with the electronic configuration anyway. So this element is in period 4. 1, 2, 3, 4. And so this is Br. That's the element. It's bromine. So we want to write the electronic configuration of bromine. We'll do the same method. So bromine, electronic configuration of bromine. Where do I want to write it? Let's put it here. Bromine. So we'll start. Period 1, we have this box and this box. So we are going to write 1s, and we counted 1, 2, 2 represent electrons. Then we go to period 2. We write the 2 here. Then the s, these are s orbitals. So how many s boxes are there? 1, 2. Represent electrons, so we'll put the 2 here. So we are not done. So we go to 2p block, you see. So we want to count the number of electrons. 1, 2, 3, 4, 5, 6. So we'll put 6. The next we want to look at, we are going to period 3. So it's 3, s block, s. How many electrons? 1, 2. We put the 2. Then we are not done with S block. S block we have. Then we go to 3p because there's no D here. Now we want to count. 1, 2, 3, 4, 5, 6. 6 electrons. Now we go to period 4. Period 4 now, we put the 4s. How many electrons? 1, 2. We put 2 electrons. Then we go put 3d because this is 3d. 3d, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We put 10 electrons. Then we go to 4p. P. 1, 2, 3, 4, 5. 5 electrons. So that is how you can use the periodic table to write electronic configuration. So you're seeing what I have done. Please try and practice. So just showing you how to write the electronic configuration for phosphorus. I think so. Oh, which one is this? So neon, and we get here. So this is, what element is this? 3sp. So neon 3sp. So we have, what element do we have here? So this should be magnesium. So this should be magnesium. So magnesium should be. So the electronic configuration of magnesium, of magnesium is neon plus 3s electrons. Okay. So let's continue. Oh. Okay, they're just going towards writing the electronic configuration of phosphorus, so we can add together. So phosphorus, we have a neon plus 3s, 2 and 3p. 3. This is the shorthand method, short form electronic configuration for phosphorus. But you know now how to write, use the periodic table to write electronic configuration, and even to come up with the short form method of writing electronic configuration for phosphorus. Please make sure in the short form, please write the noble gas configuration in a bracket, then anything outside write it. But it must be a noble gas electronic configuration first, before you can write the order. The noble gas configuration before you meet the elements. Then this represents the valence electrons, 5 electrons, those are valence electrons. So transition elements. For D block metal, the principal energy level is 1 less than the period number. So for D block metal, the principal energy level is 1 less than the period number. So for zinc, it has 30 electrons. It's in period 4. Group 2b. So its electronic configuration is argon 4s3d. So you feel the 4s before you feel the 3d, because of the penetrating power. So for F block metal, the principal energy level is 2 less than the period number. So for example, we have the element EU has atomic number 63, it's in period 6, but its F electrons are 4F. That's what we mean. So let's now write the electronic configuration for arsenic. So you see the noble gas, that's a short form. The noble gas before arsenic is argon. So you have to write argon. Then you write every other thing outside. So you see, you write argon first. Then you write 4s. Then you write 3d. Then you write 4p3. So it has 5 valence electrons. It has 5 valence electrons. The ones in 4s and 4p. The electrons in the highest energy level. So please try and practice this. Use the periodic table to write the short electronic configuration and short orbital diagram for each of the following. Practice it. Try and practice it. So this is what we are going to have. So this is a short form because neon is a noble gas before sodium. You write it in the bracket to show that the core is neon. It must be a noble gas. Then 3s. Then the valence electron is just one box spin up. Let's look at Te atomic number 52. So this is electronic configuration. The noble gas before is krypton. Then we have 5s. Then we have 4d. Then we have 5p. So it has valence electrons, the ones here, 2 and the 6. Valence electrons are 6. This and this. Then we have atomic number, Tc. Its atomic number is 43. So the noble gas before that element is K arrow. Then we have 4s2 and 4d5. But this is its valence electron. So we'll continue with the electronic configuration. There are some exceptions. So for chromium, this is what is expected, but this is what we have. Copper, this is what we expected, but this is what we have. Molybdenum, this is what is expected, but this is what we have. Ario, this is what we expected, but this is what we have. And PD, this is what we expected, and this is what we have. Why? Because here there is even distribution of the electrons in the subshell. You see, there's a balance. This is half filled, this is half filled. It's more stable than this, so it prefers this. For copper, 3D is filled. So it gives it more stability than when S is filled. So that's why it takes this form. For ammo, half filled, just like in chromium. That's why it takes the form. Here too is half filled. All of them are half filled. That's why it takes the form. So those are the exceptions, some of the exceptions we have for the electronic configuration. Let's look at electronic configuration of anions in their ground state. Anions are formed when atoms gain enough electrons. Sulfur atom has 6 valence electrons. This is sulfur atom. In order to have 8 valence electrons, so that it can be stable, it will fill its subshells, it has to pick up 2 electrons. So sulfur anion has this electronic configuration, which is just, in the short form, it has the neon core. You have this neon core. And 3s2, 3p6. So orbital diagram looks like this for the anion. Let's look at electronic configuration of cations. Electronic configuration of cations in the ground state. Cations are formed when an atom lost its valence electrons. The magnesium atom has 2 valence electrons, That's it. And when it gives this electron, when it gives these valence electrons, the cation becomes like that of, this is neon, which is much more stable than when it has 2 electrons in a subshell in a principal energy level. It wants to have a stable electronic configuration. So electronic configuration of cations in the ground state. For transition metals, electrons may also be removed from the sub-level closest to the valence electrons shell. So for example, look at iron. It will remove this 4s electron good. When it does that, it forms iron 2+. But it can remove 1 more electrons in the d. You see, the d orbital, when it has 3d, which is half filled, is more stable than when it has this. So to form iron 3+, it removes this one. And this makes it very stable. That is why it can also form F2+ and F3. You see the electronic configuration. This is half filled, which is good. Let's look at copper. Copper too, you see, it can remove this. Fine. And remains with this. But it can also have a +2. It can just be in such a way that it can remove just, it can rearrange it and remove 2 electrons before it's 2 electrons, and I have copper 2+. Either way. We want to talk about the magnetic properties. Magnetic properties of transition metal atoms and ions. Paramagnetism is when atoms or ions have unpaired electrons. That's what we term paramagnetism. They have unpaired electrons. And when they have unpaired electrons, they will be attracted to a magnetic field. Example, we have silver atoms. You see this unpaired electron. It is paramagnetic. Silver 2+ has unpaired electron. It's also paramagnetic. Diamagnetic is when atoms or ions have paired electrons, not unpaired. Their electrons are paired. These slightly repel by a magnet. They are repelled by a magnet. Silver +1 ion, you see, all its electrons are paired. So this is diamagnetic. Zinc, all the electrons are paired. It's also diamagnetic. So determine whether the following are paramagnetic or diamagnetic. So when you have unpaired electrons, remember they are paramagnetic, they are attracted by a magnet. But when the electrons are paired, it is diamagnetic. They are repelled, almost repelled by a magnet. Let's look at magnesium. And in order to do that, we need the orbital diagram. If you don't have the orbital diagram, you will not be able to know whether the electrons are paired or not. So you have to write the orbital diagram, especially of the valence electrons. So let's look at the orbital diagram of manganese. So this is manganese, argon core 4s2 3d5. So let's look at the orbital diagram of the valence electron. It has unpaired electrons. So manganese is paramagnetic. Let's look at scandium 3+. You see, this is scandium. To form 3+, it gives this and this. So scandium 3+ is diamagnetic. It doesn't have unpaired electrons. So please try and do some practice. Write the electron configuration and determine whether iron atom or iron 3+ ion are paramagnetic or diamagnetic. So we are going to stop here. Please make sure you do this practice. It's going to help you understand the course better and understand this section well. Write the electronic configuration, then write the orbital diagram. If you see any unpaired electron, it means it will be paramagnetic, it will be magneted by a magnet. But if you see paired electrons, it will be diamagnetic and it will not be attracted to a magnet. We are going to continue from here.